introduce the third speaker for today, which is also a joint paper by two speakers, Dr. Salma and Dr. Reese. You will introduce our speaker, her co-speaker. Dr. Salma is she's an academics from the University of Science and Technology in Sudan, and her co-author, she will introduce her co-author. They have been doing quite a lot of good work on sustainability, particularly about cement, sustainable production of cement. She's going to talk to us more technical about one of the, yesterday they talked about the trials. So Dr. Salma, because of the time, I will give you the floor.
Welcome everybody to our presentation. My name is Salma Mahmoud and my colleague Eltahir A. We're trying to investigate the behavior of calcined kaolinite clays from Sudan as a sustainable cementitious material. The presentation, I'll cover a brief, I'll give a brief introduction and then state the problem, outlining some of the objectives, and I will give a brief account on the kaolinite clay in Sudan, their origin, structure, and availability. And then I'll focus on the experimental work that we conducted, giving you at the end of the presentation a conclusion and some recommendations. Right, Sudan, the construction industry in Sudan, as in many developing countries, suffers from a multitude of challenges. These challenges confront the development and the performance improvement of the industry. And for the problems related to the materials, the construction materials, construction and building materials, their production, their supply, and their management, this problem tend to dominate the list of impediments towards the industry improvement. So the building construction process basically involves the usage of several materials. Some of them are natural, others are man-made. And because of the appearance of new trends in building architectural and structural designs, more man-made materials came into the scene with more sophisticated properties to match the client's requirements for more durable, cheaper, and ecologically friendly options. Concrete, which is the most widely man-made structural material. It's a composite material that is mainly containing aggregates in their two different forms, the fine and coarse aggregate, as well as cement, water added in different proportions, and maybe sometimes we add some admixtures for certain properties. However, concrete is criticized for being an environmentally unfriendly material. The production of concrete involves the use of cement, and cement production is one of the main problems that for the carbon dioxide emission. The production of cement involves depletion to the natural resources during the process of the raw materials extraction and processing. And also the concrete transportation consumes energy and poses some pollution to the environment as well. So this means that the impact of concrete production to the whole environment, it destroys the natural infrastructure without replacing the ecological functions that humanity depend on. So our aim concerning this part of our research is to find environmentally friendly materials, to find, to look for more comparable options, and to look for something that is sustainable, but at the same time could do the same job that the components of the concrete mix can do. So we basically were thinking to go green. Our objectives are as follows. We wanted to explore the availability of kaolinite clays as a naturally occurring mineral in Sudan, and we wanted to prepare metakaolin, which is a thermally treated form of the kaolinite clay. And we wanted to determine the chemical composition of this metakaolin and to assess their pozzolanic reactivity, because we're going to use them in replacement for cement in different types of concrete mixtures, so that we can determine whether it's a suitable material or not. So the methodology that we basically adopted was as follows. The kaolinite clay was collected from 4 different locations in Sudan for this study. And after that, we transformed the kaolin clay to metakaolin through a calcination process. Then we checked the chemical composition to determine the major oxides which were available in this form of material, and compare that to ordinary Portland cement. As well, we wanted to determine the degree of pozzolanicity for this new material before using that in different ways in concrete mixtures. As for the kaolinite clay collection, the kaolin, which is the China clay, it's a hydrated aluminum silicate crystalline mineral, which is called or referred to as kaolinite. Its physical appearance, when we collected these samples from the field, it's just like sometimes it's a powder, other times it gets in like larger pieces, whitish in color in some places, and in other places, the color is brownish, light brown, or maybe yellowish or grayish. All in all, it does not dissolve in water, but when it gets wet, it gets darker in color, and it gets an earthy smell. Chemically, the kaolinite clays are structured around a series of alternating buckled silicate and aluminate layers, with the silicon in 4 coordination and the aluminum in a mixture of 5, 4, or 6 coordination. In Sudan, it was found out that kaolinite clay is available in many different areas, extending all over the country. We've got samples of kaolinite clays in the Red Sea Hills in the northern Sudan. We've got some in northern Kordofan in the western part of Sudan. We've got some in the northern parts of Sudan, in Shendi, we've got in Gadarif, Shuak, even in the central parts of Sudan. So it's available in many locations in Sudan. The process of getting the metakaolin, which is the material that we are going to incorporate in our concrete mixtures, we had to treat the kaolinite clay in a thermal way. So it's a very simple and basic process where the mineral kaolinite was heated. Upon heating, this process drives the water up and collapsing the material structure. The ending result is an amorphous aluminosilicate, which is the metakaolin that we are trying to use in our concrete mixtures. Right. For us in the lab, the kaolinite clays were heated for 5 hours in temperatures ranging from 700 to 800 degrees Celsius in a very simple furnace in the lab. And after that, the process was followed by grinding it in high capacity mills to produce very fine particles, because basically we are trying to mimic the fineness of cement in our concrete mixtures. As for the obtained sample of the metakaolin, we had to check the chemical composition of the material by determining the oxides present in our samples. So we were focusing on the major oxides because we're trying to compare that to ordinary Portland cement. So the samples obtained from 4 different locations, Marawi, Kassala, Garri, As-Sayyal in Sudan, we had the analysis, and then that was compared to the major oxide considering 3 different standards: the Sudanese manufacturers and the limits according to the ASTM, as well as the limits according to the British standard. On top of this, we had to check the pozzolanicity and the limit according to the limit set by the ASTM C618. So what we found out is that the kaolinite clay are very rich in oxides that are of interest to us when we study cement. So after checking the suitability of the produced or the calcined kaolinite clay in comparison to ordinary Portland cement, we wanted to use that in our concrete mixture. So 3 suggested scenarios were explored to visualize the possible outcomes. We had the metakaolin to produce normal concrete, and once again to produce high strength concrete, and then producing self-compacting concrete. So with the first scenario, the metakaolin was added in concrete mixtures in different percentages. We started with 5, and then topping it up to 10, 15, 20, and 30% in replacement for cement. Right. And we checked after that the compressive strength. We checked the compressive strength for the different samples in different curing ages. As for the first sample, we had it for 7 days, 28 days, and even we studied the long-term effect of this material in our mix. And we were able to get results exceeding the targeted strength for the first sample. As for the second sample, or the first design, we had 7, 14, and 28 days, and we were also able to get compressive strength, which is matching the required or even getting higher than the targeted strength. The same applied for the last sample from another location, and it gave us the same results. For the second scenario, incorporating metakaolin to partially replace cement to produce self-compacting concrete, three mixed trials were conducted, where the first trial was not successful, and for the second and third trials, we were able to get self-compacted concrete. We had the fresh concrete test for the slump flow, for the V-funnel test, and then for the viscosity test, as well as the hardened concrete properties, we checked the compressive strength. So for the third scenario, we had the metakaolin partially replacing cement, but this time producing high-strength concrete. So we had all the fresh concrete tests as well as the hardened concrete test. For the fresh concrete test, the results were within the required set limits, and for the compressive strength for the hardened concrete samples, we were able to get the compressive strength in the range of 53 to 63 megapascal, and by that exceeding even the targeted strength. So what can we say out of all these experimental work and experimental results? The kaolinite clays are abundant, and they are present in different locations in Sudan. And that makes it one of the most important aspects. The other thing is that the chemical characterization of the metakaolin showed us the presence of high amounts of silica, alumina, and iron oxides. The percentages are even exceeding the limit set for cement by the 3 standards that we consulted. And these are the major oxides that we are looking for. At this point, we were very happy with these amounts, and we were expecting good results, as these are early indications for the suitability of this material. Also, we found out that the presence of magnesium oxide and the loss on ignition values were all within the set limits for all the consulted standards. It was also evident the possibility of producing normal concrete, high-strength concrete, and self-compacting concrete. The 3 forms or the 3 scenarios that we investigated, we were able to get good results out of the use of the metakaolin. We found out that the location from which we got the source kaolinite clay makes a difference. For example, Casalas metakaolin yielded the targeted strength in 28 days, with an optimum amount of only 5% of metakaolin replacing cement, while from another location, which is Gary, the metakaolin yielded just a slightly higher than the targeted strength, with the same amount of metakaolin replacing cement. And when we had the metakaolin included in self-compacted mixtures, that was interesting. All the slump flow test results confirmed the suitability for the different types of structures being slightly reinforced for vertical application or normal application, while the other test, which is the viscosity measurement, showed a medium rate flow, whereas the 28 days compressive strength had further confirmed that the trial mixtures meet the targeted value. It was also possible to achieve high strength values, values for the concrete that included metakaolin, and we got up to 63 megapascal when metakaolin was included in the range of 10 to 20 in replacement for cement. So what can we say out of our results or our experimental work? Because we had so many samples, different ages, different metakaolin from different locations. We had the metakaolin processed at different temperatures. So we had a lot of experimental work, and all these results gave us reasonable evidence for the usefulness of this material to be a sustainable cementitious material, because at one hand, it gives us the required properties that we need in our concrete. And at the same time, it's just like, it's an available, abundant, it doesn't really need chemical treatment or processing, or it does not deplete the virgin, the environment. So we're not harming the environment. We are getting what we want for the concrete that we are producing. So we were quite happy with this material to be used for concrete. as a cementitious material. And I think we've got, still we've got more and more experimental work on it to have it like in different types or more types of concrete and studying it at longer ages. But the results until this point gave us very reasonable evidence that this could be one of the sustainable construction materials. Thank you very much for your attention.
Thank you very much, Dr. Salma. Now let's open the question. Let's open it for question and answer now. Because I've been following this on the social media. By the way, there's a very good coverage in the social media. Now, Dr. Salma, let me just unmute you first to make sure. Can you unmute yourself? Yes. Dr. Salma, the question we always ask with all technology, all new approaches, all new applications for the production of any kind of products, chemicals, whatever we do, on the sustainability, we ask about the economic and social visibility. To what extent socially and economically, because many people, engineers can understand your engineering discussion on the paper very well, but for those from the social science, they will be very keen on two things. How visible this, I know you have explained that in the paper to some extent, but if you can just give people in economic terms, do you think that's going to be, like, just give you example, like wheat production. Wheat is where we get our bread, we need wheat. But many people, scientists, have been working quite closely to minimize the usage of wheat in the making of bread to try to get maize and other kind of grains. So that means you can, because you need to make sure it is still have that glue factor, but at the same time, it is economically visible. To what extent what you're proposing is economically going to work? Let's assume you succeeded in all your experiment eventually, and we want to apply it. Maybe the industry sector, they will say to you, is good, doctor, but it's not visible. We're not going to get money from it. The same like renewable and green energy and all these things. They are in the UK, they're expensive. Green energy is not cheap. To change this house into solar and green, it can work, but it is, that's why the government is paying money as a grant for people. So in your case, is it going to be economically visible?
Well, this is one of the most important things, is to see the economics of the whole concept. But we were not able to get you an exact figure because the way we treated the clay, to be able to use it to substitute cement, we were using very basic equipment to produce that. So even if we were going to calculate the cost for that, it's not going to give us the exact or true value, because if we want to use the metakaolin in large scale to replace cement, we have to prepare the metakaolin and produce it like the cement. So we will have, like, maybe if we're producing large amounts, then we're not getting very expensive products, like the concept of the economy of the scale or so. But because we are doing it in very small amounts now, the costs that we are calculating are not the true ones, because we had to go somewhere to make the calcination process, and that will add to the cost because we pay for that in a different way. We have to get the raw material itself is not costly. It's just abundant, it's everywhere. We just go and collect it. So this is not costly at all. But we didn't really get exact figures calculated to let you know that the cost of using metakaolin is going to be X, while the corresponding cost in case of using cement is going to be X, because the cement is a well-known process and we can calculate that, or we have the figures. But for the metakaolin, we don't really have the figures yet, to be honest.
Thank you very much, Dr. Salma. But the important thing, you are a scientist or an engineer, you're taking that into account, because this is what we always try to make sure. When people work in multidisciplinary team, we say it's important, we bring this to you. We are economists, you are a scientist, you are engineer. So we want to take care of because we don't want to end up in a result, producing good result, but people, they will say to you, it's very expensive. Now, if there is any other final question, because we're really running out of time on this session, apologies for these technical issues, but at least we managed to get all the three presentations. The good thing is all this presentation, Mervin and his team, they will edit them and they will make them, and they will, we will then be able to customize them, and they will be shown on a separate lecture. So you will see them, all of them. If there's any other final question, I'm just trying to look. If there's any, press on that yellow hand if you have any question. I can't see any other question. I think we're slightly over our time. It's almost 1 o'clock. Now we're going to give you a half an hour break. But before we do that, I would like you to join me in thanking all our 3 distinguished speakers. We had Sunday Olodigi from Nigeria, also Salami, Michael from Nigeria. We had earlier Dr. Mohra from UAE, and we had finally, last not least, Dr. Salma and her co-author from Sudan. If you could all join me in thanking them, I think we have to clap for them because I think they have done a wonderful job. We wish if they were physically here, we can have said thank you to all of them. But it has been a very informative, very useful 3 presentation. Thank you very much, and I wish you all the best. We will stop for half an hour because we have a lunch break, but we are technically back at 4 o'clock with 3 very good papers. I think they want to talk about technology. We have, I can quickly just remind you what we have at 4 o'clock. We have Disruptive Technologies, Livelihood and Education by Monica and Larry from the US, the entertainment industry, both COVID-19 in developing countries, developing technologies and new approaches from Nigeria. And then we have a paper about e-learning in accounting education from Libya. And then at 6:30, we have 3 papers, one from UCL, Impact of COVID on Black and minority ethnic female health care. We have Social Impact of Community Resilience by Olivia. And then we have the impact of COVID-19 on ethnic minorities. So I will leave you now. We'll see you at 4 o'clock. Thank you very much. And please stay safe and adopt this social distancing. All the best.
So please remember, if we all help and do a little bit, it will make a big difference.